Good day, and welcome to this special holiday deep dive. It is December 24th, 2025. Across the globe, billions are settling in for Christmas Eve celebrations. The lights are dimming, and the year is winding down. But here, at the Space Science Desk, the screens are brighter than ever. While the world looks inward to family and tradition, a dedicated cadre of astronomers, geophysicists, and data analysts are looking outward, locked in a fierce debate that has only intensified in the last 96 hours. We are talking, of course, about the interstellar object 3I Atlas, also designated as C2025N1. If you thought the story of this visitor ended when it silently slipped past us earlier this week, you would be mistaken. In fact, the story is just beginning. Let's look closer at the data. 5 days ago, on December 19, 2025, 3I Atlas reached its point of closest approach to Earth. It was a moment anticipated for months, a gravitational keyhole that offered us the best look we would ever get at this traveler from another star system. Telescopes from the Atacama Desert to the high peaks of Hawaii were trained on its trajectory. We expected high-resolution light curves. We expected spectral analysis of its surface composition. We expected, frankly, a quiet confirmation of its cometary or asteroidal nature. What we got instead was a fractured consensus and a scientific community that is currently split down the middle. As we sit here on Christmas Eve, the data streaming in isn't resolving the mystery, it is deepening it. Before we dive into the specific anomalies that have surfaced in the last few days, if you appreciate this kind of rigorous, data-first analysis of space science news, make sure to hit that subscribe button. We track these stories not just when they break, but as they evolve, and you won't want to miss the updates coming in the next few weeks as 3I Atlas heads toward the outer solar system. Now, to understand why this flyby has become so contentious, we have to strip away the headlines and look at the raw timeline. The object's approach was standard. Its orbital mechanics were, for the most part, obeying the laws of Kepler and Newton. But as it swung by Earth on the 19th, the observational silence was broken by a claim that has since rippled through the alternative science communities and is now knocking on the doors of mainstream academia. This wasn't a visual anomaly. It wasn't a sudden brightening or a fragmentation event, which are common for comets under solar stress. This was something invisible, something that speaks to the fundamental electromagnetic environment of our own planet. The narrative that has dominated the last few days centers on a series of conflicting observations. On one hand, we have the rigid, silent data from radio telescopes earlier in the year, which we will get to, suggesting this object is as inert as a rock. On the other hand, we have new emergent data from the moment of closest approach that suggests 3I Atlas might be interacting with Earth's magnetosphere in ways we didn't predict. This contradicts what we previously thought about the passive nature of small interstellar bodies. Usually, a rock is just a rock. It reflects sunlight. It might outgas a little water vapor or carbon monoxide, but it doesn't speak. It doesn't broadcast. Yet, the reports coming in from independent researchers suggest that for a brief window during the flyby, the electromagnetic silence was broken. We need to be very precise here. When we talk about signals in this context, the public imagination immediately jumps to aliens, to communication, to hello. But in science, A signal is simply a deviation from the noise. It is a pattern where there should be randomness. The debate raging today isn't necessarily about little green men. It's about physics. It's about whether an interstellar object traveling at hypervelocity can induce a resonance in the Earth's own ionosphere, or if what we are seeing is a coincidence of massive proportions. The timing is the first variable we have to isolate. The object reached its minimum distance on December 19th, but the event of interest, the spark, if you will, reportedly occurred hours before that mathematical moment of closest approach. This is a crucial detail. If 3I Atlas were emitting a constant beacon, we would have seen it for weeks. We didn't. If it were a simple reflection of solar radar, it would follow a predictable geometric curve. It didn't. The anomaly was transient. It appeared, it spiked, and it vanished. This transient nature is what makes it so difficult to verify and so easy to dismiss. But it is also what makes it impossible to ignore. Imagine the Earth not just as a rock, but as a giant magnetic bell. The atmosphere and the ionosphere form a cavity, a space where electromagnetic waves bounce around. Usually, this bell rings with the chaotic strikes of lightning storms, thousands of them happening every second around the globe. This creates a hum, a background static that we call the Schumann resonances. It is the heartbeat of the planet's electric circuit. The claim on the table is that 3I Atlas didn't just fly past the bell, it struck it. Or, more disturbingly, that it hummed in harmony with it. As we move through this investigation, we are going to dissect the specific frequency of this hum. We are going to look at the exact timestamp, 02.40 UTC, and we are going to ask why a geologist, not an astronomer, was the one to catch it. This is a story about the intersection of two very different fields, the study of the stars and the study of the ground beneath our feet. It turns out that looking up and looking down might have revealed the same mystery. So, what does this actually mean for our understanding of 3I Atlas? It means that the standard model of this object, a frozen chunk of nitrogen or hydrogen ice tumbling through the dark, is facing a stress test. We have to reconcile the visual silence with the electromagnetic noise. We have to understand how an object could be radio quiet in the gigahertz range, as confirmed by our most powerful arrays, yet apparently scream in the extremely low frequency range, just as it brushed past our planet. The holiday season is usually a time for quiet reflection. But for the scientist analyzing the terabytes of data from December 19th, there is no quiet. There is only the noise, the signal, and the desperate attempt to separate the two. As we peel back the layers of this encounter, remember that in science, the most exciting phrase isn't eureka, but that's funny. And right now, looking at the data from the 19th, there are a lot of people saying, that's funny. This brings us to the specific mechanism of the claim. To understand the anomaly, we have to understand the instrument that detected it. We have to leave the high-altitude observatories and go down to the ground level, to the induction coils and the magnetic sensors. We have to talk about Stefan Burns. As we established in the previous chapter, the flyby of 3I Atlas on December 19th was not the quiet, purely visual event many astronomers had predicted. While the optical telescopes were tracking a faint point of light, moving against the background stars. A different kind of listening was happening on the ground. A listening directed not at the gigahertz frequencies of deep space communications, but at the extremely low frequencies, or ELOF, that pulse through the Earth's own atmosphere. This is where the narrative shifts from the stars to the sensors, and specifically to the observations of American geologist Stephen Burns. Let's look closer at the data Burns has presented. While the world was watching the countdown to the closest approach, Burns was monitoring the Earth's electromagnetic heartbeat. His claim centers on a specific timestamp, 0240 UTC on December 19, 2025. To put this in context, this is approximately 3 hours and 20 minutes before 3I Atlas reached its absolute minimum distance to Earth. In orbital dynamics, this is close quarters. The object was barreling through the inner solar system, dragging its gravitational and potentially electromagnetic influence with it. It was in this window, Burns asserts, that his instruments recorded a distinct electromagnetic anomaly. Now, you might be asking, what does an anomaly look like on a graph? Usually, when we look at LF data, we see chaos. We see the jagged, random spikes of global lightning activity. Lightning is a broadband emitter. It splashes energy across a wide range of frequencies like a stone thrown into a pond, creating messy, overlapping ripples. But Burns insists that what he saw was not a splash. It was a laser beam. He reported a signal that was narrowband and sharply concentrated. It didn't wander. It didn't fuzz out. It sat, unwavering, at exactly 25 Hertz. Here is the crucial detail. 25 Hertz is not a random number. It sits squarely within the band of the Schumann resonances. For those who might not be familiar, the Schumann resonances are a set of spectrum peaks in the extremely low-frequency portion of the Earth's electromagnetic field spectrum. They are global electromagnetic resonances generated and excited by lightning discharges in the cavity formed by the Earth's surface and the ionosphere. The fundamental frequency is usually cited as 7.83 Hertz, with harmonics, or overtones, at roughly 14, 20, 26, 33, 39, and 45 Hertz. So, a signal at 25 Hertz is right in the neighborhood of the third harmonic. But, and this is a massive but, natural Schumann resonances are not sharp lines. They are broad peaks. They breathe. They fluctuate with the time of day, with solar activity, with the global temperature. A natural resonance at 25 Hertz should look like a gentle hill on a graph. Burns describes his detection as a spike, a needle in the haystack. He emphasized that this signal differed significantly from typical atmospheric disturbances. It lacked the noise of nature. It looked, for lack of a better word, artificial. Or, at the very least, it looked like a driven oscillation, something being pushed by an external force rather than just ringing naturally. This contradicts what we previously thought about the interaction between interstellar objects and Earth. We generally assume these objects are electrically neutral, or at least not charged enough to drive a current in the Earth's ionosphere from a distance. But if 3I Atlas were carrying a significant plasma tail, or if it possessed a strong intrinsic magnetic field, something rare for small bodies, it is theoretically possible it could induce a perturbation. However, a perturbation usually looks like a wave, a distortion. It rarely looks like a pure 25 Hertz tone. Burns' observation at Uro 240 UTC implies a synchronization. It suggests that as the object neared, something locked on. The signal appeared, held steady, and then presumably faded or was lost as the geometry changed. This behavior is what makes the claim so electrifying and so frustrating. If it were a continuous emission, other stations would have picked it up. But because it was transient, appearing only shortly before maximum proximity, it exists in that gray zone of unverified single-source data. However, we cannot simply dismiss it as equipment error without looking at the context. Burns is not claiming this was a radio message. He is not claiming he decoded a greeting. He is pointing to a physical interaction. He is suggesting that the object acted as a trigger. And this is where the story gets even more complex. Because 25 Hertz isn't just a frequency in the sky. It's a frequency that has been whispered about in the ground. Burns didn't just report this as a space weather event. He immediately drew a connection to the solid Earth. He argued that this frequency lies within a range that some researchers have previously linked to potential earthquake precursors. This is a bold leap. It moves the discussion from interesting space anomaly to potential planetary hazard. He pointed to a similar electromagnetic anomaly, a ghost signal, that was allegedly detected several days before the powerful earthquake that struck Japan earlier this month on December 8, 2025. So, what does this actually mean? Are we looking at a coincidence, a sensor glitch, or are we seeing a coupling between an interstellar flyby, the ionosphere, and the tectonic plates? The idea seems like science fiction, but the data point at 25 Hertz stands there, stark and unexplained. It challenges us to ask if our monitoring of these objects has been too narrow. We have been looking for light. We have been looking for heat. Maybe we should have been listening for the hum. As we move to the next chapter of this investigation, we need to rigorously examine this seismic link. Is there any science to back up the idea that a 25 Hertz signal can predict an earthquake? Or is this a case of finding patterns in the noise where none exist? The connection to the Japan quake is the most controversial part of Burns' hypothesis, and it demands a skeptical, hard-nosed look. Building on this detection of the 25 Hertz anomaly, we find ourselves wading into one of the most contentious waters in geophysics, the prediction of earthquakes. Stefan Burns didn't just leave the data as a curiosity of the ionosphere. He anchored it to the crust. By linking the 25 Hertz signal observed during the 3I Atlas flyby to the seismic event in Japan on December 8, 2025, he has ignited a debate that goes far beyond astronomy. Let's look closer at the data regarding this seismic connection. The earthquake in Japan on December 8th was a significant event, a powerful tremor that reminded the world of the Pacific Rim's volatility. In the aftermath, as is common, researchers scrambled to find precursors, warning signs that might have been missed. Burns claims that a similar electromagnetic anomaly, resonating in that same low-frequency band, preceded the rupture. His argument relies on the concept of lithosphere-atmosphere, ionosphere coupling. The theory goes that before a major quake, the immense stress building up in the rock creates microfractures. These fractures can release ionized gas or generate piezoelectric currents, which then propagate up into the atmosphere and perturb the ionosphere. If, and it is a massive if, this mechanism is real, then a spike at 25 Hertz could theoretically be a scream from the rocks before they break. Burns is suggesting that the signal detected during the flyby of 3I Atlas shares a fingerprint with these terrestrial warning signs. But here is the crucial detail that complicates his narrative. The Japan quake happened weeks before the flyby. The signal Burns detected on December 19th happened when the object was closest. Is he suggesting the object caused the quake retroactively? No. He is suggesting that the type of signal is the key. He is arguing that 3I Atlas might be an active body, geologically or electromagnetically, capable of generating the same kind of stress signal that a shifting tectonic plate generates. This contradicts what we previously thought about the isolation of these systems. Mainstream geophysics remains highly skeptical of electromagnetic earthquake precursors. For decades, scientists have hunted for a reliable silver bullet signal, be it radon gas, animal behavior, or radio waves. While there have been intriguing anecdotal cases, the existence of a reliable causal relationship between seismic events, low-frequency electromagnetic signals, and astronomical phenomena remains highly controversial and unproven within the broader geophysical community. The consensus is that while the ionosphere can be disturbed by earthquakes after the fact due to acoustic waves, the idea that the ionosphere predicts the quake with a specific 25 Hertz tone is not supported by robust, repeatable data. So, what does this actually mean for the 3I Atlas story? It means we have a correlation problem. We have a sample size of one flyby and one earthquake. Burns is drawing a line between two dots that are separated by time and space. The skepticism from the scientific community is not just stubbornness. It is a defense against false patterns. If we accept that 3I Atlas emitted a seismic-like signal, we have to explain the mechanism. Is the object under stress? Is it vibrating? Or is it inducing stress in the Earth? There is no evidence that 3I Atlas triggered any seismic activity on Earth during its flyby. The ground did not shake when the signal appeared at 240 UTC. This absence of a physical quake during the flyby actually weakens the direct link. If the signal is a precursor, where is the event? Unless, of course, the signal was the event, a purely electromagnetic interaction that mimicked the signature of a quake without the physical rupture. Before we go further, I want to hear from you. Do you think science is too quick to dismiss these fringe correlations, or is it right to demand extraordinary proof for such extraordinary claims? Drop a comment below with your take on the Burns hypothesis. Is it a breakthrough or a distraction? This connects to the broader problem of confirmation bias. When a mysterious object enters the solar system, we tend to project our current fears and mysteries onto it. In 2025, with solar activity high and seismic nerves rattled, it is natural to look at the intruder and ask, "Did you do this?" But science demands we look at the null hypothesis. The null hypothesis says the 25 Hertz signal was a local interference, a power grid fluctuation, a military submarine communication, which often uses ELF, or a sensor artifact that just happened to coincide with the flyby. However, even if we strip away the earthquake theory, the 25 Hertz signal remains a data point that refuses to fit the curve. It stands in stark contrast to the other major data set we have on this object. While Burns was looking at the low frequencies of the Earth, astronomers had previously scoured the high frequencies of the cosmos, and their results painted a very different picture of 3I Atlas. To understand the full paradox of this object, we have to rewind the clock back to July, long before the Christmas flyby, when 3I Atlas was still a distant speck. The heavy hitters of radio astronomy took a shot at it. They weren't looking for earthquake signals. They were looking for technology. And what they found, or rather, what they didn't find, creates a fascinating tension with the new claims. We need to examine the gigahertz silence. Given what we now understand about the low-frequency anomalies reported during the December flyby, we must pivot to the other side of the spectrum. Science is rarely about a single observation. It is about the synthesis of conflicting data sets, and the claims of a 25 Hertz hum stand in apparent contradiction to results obtained earlier in 2025 through one of the most comprehensive radioastronomical surveys ever conducted on an interstellar visitor. Let's look closer at the data from the Allen Telescope Array, ATA. Situated in the cascade of radio-quiet mountains in California, the ATA is a hunter. Its prey is the artificial, the technological, the non-natural. On July 2, 2025, months before 3I Atlas would graze the Earth, astronomers initiated a targeted 7.25-hour observing campaign. The object was distant, faint, and moving against the cosmic backdrop, but the ATA locked on. The scope of this survey was massive. They didn't just listen to a single channel. They scanned 3I Atlas across a wide frequency range from 1 to 9 gigahertz. This is the microwave window, the water hole of the universe, where the background noise of the galaxy is quietest, and where humanity, and presumably other intelligences, would conduct long-range communication. If 3I Atlas were a probe, a ship, or a piece of active technology, this is where it should have been screaming. The initial raw data was overwhelming. The survey yielded nearly 74 million candidate signals. This number sounds staggering, but in radio astronomy, candidate just means a blip above the threshold. It includes satellites, cell phones, aircraft radar, and the thermal hiss of the telescope itself. The real work is in the filtration. Here is the crucial detail. The team applied extensive filtering designed to eliminate terrestrial radio interference. They looked for signals that moved with the object. If a signal is from Earth, it stays fixed relative to the ground. If a signal is from 3I Atlas, it must drift across the sky, matching the precise Keplerian orbit of the intruder. After this rigorous Doppler sifting, the 74 million candidates evaporated. Only 211 signals remained. 211 sparks in the dark. Each one was a potential hello. But science is ruthless. A subsequent visual inspection of these candidates, looking at their spectral shape, their timing, their persistence, failed to identify any emissions consistent with a technosignature. There were no prime number sequences, no narrowband carriers that defied explanation, no artificial transmission worthy of further investigation. The 211 survivors were dismissed as statistical flukes or subtle interference. So, what does this actually mean? It allowed researchers to set a hard upper limit on the object's possible emission power. They calculated that if 3I Atlas were transmitting, its power was estimated to fall between 10 and 110 watts. Think about that. A standard light bulb, an omnidirectional transmitter on 3I Atlas with the power of a reading lamp would have been detected. The silence was deafening. These findings were later discussed publicly by Harvard astrophysicist Avi Loeb. Known for his provocative hypotheses regarding Oumuamua, Loeb is not one to shy away from artificial explanations. Yet, in this case, he noted in his blog that despite widespread speculation, the radio data collected so far provide no evidence of artificial activity associated with the interstellar object. When the leading proponent of extraterrestrial archaeology says the radio line is dead, it carries weight. This creates a profound tension in our narrative. How do we reconcile the gigahertz silence of July with the Schumann hum of December? Are they mutually exclusive? Not necessarily. The ATA looked for high-frequency communications, the kind used for data transfer. Burns looked at low-frequency resonance, the kind associated with magnetic interaction or propulsion byproducts. It is possible for an object to be radio silent in the gigahertz range, no Wi-Fi, no telemetry, but electromagnetically active in the ELF range, magnetic braking plasma interaction. However, the simplest explanation is often the correct one. The ATA data is robust, peer-reviewed, and statistically significant. The Burns data is singular, transient, and entangled with controversial earthquake theories. The silence is the baseline. The hum is the outlier. But the story of 3I Atlas didn't end with the radio silence. It didn't end with the flyby. As the object swung past Earth, it did something that no radio telescope could miss and no geologist could ignore. It moved, and it moved in a way that is now setting up the final act of this cosmic drama. The object is no longer heading toward us. It is fleeing, and its destination is the king of the solar system. As we track 3I Atlas on its outbound leg, we are seeing an acceleration. It is picking up speed as it moves away from the Sun. This non-gravitational acceleration is the hallmark of comets, jets of gas pushing the rock like thrusters, but without a visible tail, without the coma that usually accompanies such speed. The mechanism remains hidden. And now, the trajectory is taking it toward a rendezvous that feels almost scripted. It is heading toward the region of Jupiter. As we established, the mystery of 3I Atlas is defined by what we don't see as much as what we do. We have the silence in the gigahertz range, the controversial hum in the low frequencies, and now, as the object recedes into the darkness, we have the trajectory itself. After its close encounter with Earth, 3I Atlas continued its passage through the solar system. But it is not drifting passively, it is accelerating. Let's look closer at the data on this departure. As 3I Atlas moves away from the Sun, it should be slowing down, fighting the gravitational pull of our star. Instead, it is exhibiting a slight, persistent push. In comets, we call this outgassing, ice sublimating into gas and acting like a rocket engine. But 3I Atlas remains stubbornly point-like. Deep exposure images show no sprawling tail, no fuzzy coma. It is a dark, compact accelerator. This dark propulsion keeps the artificiality debate alive. If it's not gas, what is pushing it? Solar radiation pressure? A magnetic sail? Or simply outgassing that is too faint or transparent for our current sensors to resolve? This connects to the final destination of our visitor. The calculated path is heading toward the region of Jupiter. Current orbital models suggest it will pass near one of the planet's moons before eventually leaving the solar system entirely. This Jupiter intercept is a poetic, if accidental, finale. Jupiter is the vacuum cleaner of the solar system, its massive gravity usually swallowing or ejecting comets. For 3I Atlas to thread the needle, passing Earth and then brushing past the Jovian system, offers one last opportunity for study. The Jupiter flyby will be distant, but the interaction with the giant planet's intense radiation belts and magnetic field could be the ultimate stress test. If 3I Atlas reacted to Earth's relatively weak magnetosphere with a 25 Hertz hum, what will it do when it hits the magnetic monster that is Jupiter? Will it light up? Will it shift course again? Astronomers are already booking time on the James Webb Space Telescope and the upcoming ground-based giants to watch this exit. So, what does this actually mean for us? 3I Atlas is once again highlighting how rare interstellar visitors can challenge existing assumptions while still yielding more questions than answers. It came, it baffled us, and it is leaving. It leaves behind a fractured data set, a clean radio survey, a messy low-frequency claim, and a trajectory that defies simple gravity. We are left with a puzzle that may never be fully solved. Was it a shard of a nitrogen iceberg, invisible to radar but active enough to accelerate? Was it a piece of debris from a broken Dyson sphere, silent but magnetically charged? Or was it just a rock, and we, in our desperation for connection, projected our own signals onto it? The beauty of science is that the file is never truly closed. The data collected on December 19th, the ATA scans from July, and the upcoming Jupiter observations will be mined for decades. Graduate students not yet born will write theses on the Christmas visitor of 2025. If you enjoyed this deep dive into the unknown, if you value news that respects your intelligence and explores the edges of what we know, please hit that like button. It helps this content find other curious minds in the algorithm. And keep your eyes on the skies, because the universe is full of things that don't knock before entering.